as we look at this portion of our periodic table, and we focus on uranium down here in the actinide series here. This is just a portion. We have 3 portions of this there, and atomic number 92, atomic weight of 238.08, something like that. Yeah, and with an electronic configuration of radon 5f36d17s2. Once again, commemorating our professor here from City College, Professor Morrow, who had a vision, and he doctored me during our telephone conversation. Can never forget. In the course was 103 was way back here in 1978, I believe. Chemistry 103 and Chemistry 108 with laboratory. But he doctored me probably in the 1980s, 90s there, I believe, when I was requesting my grades, my comprehensive profile, and he called me. So I do believe he has a vision there, Professor Morrow or Professor Dr. Morrow, whichever one is more relevant for optimization. And so here we are with uranium. Well, I scored a A for that course, really, at the laboratory. And but in 108 I scored a C plus due to I didn't turn up for my laboratory there for some reason, but that was supervised by Professor Rader. Okay, from the City College. We are at uranium, and so we continue uranium, and we have this uranium dioxide, or UO2, uranium oxide, and we have U with a double bond of oxygen there, 2 double bond, U double bond O on the right and U double bond O on the left. And the nuclear disintegration of U238 form radon 226. I think I saw radon here a while ago. That's uranium, that's barium. We'll use all of these. I don't know where my radon turns up here. Oh, use radon, and it does have, this one is radon 222 though. This, I believe, is the most stable radon, and 86. But the one from this nuclear reaction, the disintegration of U238 is a radon 226, which disintegrate to form radon gas, Ra222, again, which is this one. So it goes from radon 226 to radon 222. And because there's isotope, the atomic number of radon remain constant, with 86. For isotope, it's the same atomic number, but different atomic mass or different atomic weights. Now, radon always decays to form a series of daughter nucleus, most of which are alpha particle releasing isotopes, such as plutonium, or really polonium-210. And polonium is more radioactive than plutonium, but the most radioactive substance around is really radium. Not radon, but radium. That's the most radioactive substance around. But polonium-210 is released via alpha particles. And then uranium-238 plus 1 neutron will yield uranium-239, which is a heavier uranium, and this new nucleus may decay to a new nuclei. So there we have a series of changes there in these reactions, in which we have this isotope such as polonium, which is more radioactive than plutonium, polonium-210, and then we have uranium-238 plus 1 neutron yielding uranium-239, and this new nucleus may decay into a new nuclei. Now, fission reaction of uranium, the original U-235 nucleus absorbs a neutron, splits into krypton-92 nucleus and a barium-141 nucleus, and releases 3 more neutrons. Now, upon splitting, what happened is that those 3 neutrons are then able to cause the fission of 3 more U-235 nuclei, and each of which now releases more nucleons, more neutrons, and so on, and so on, and so on. And then you have this sort of a chain reaction. Now, uranium bombarding the U-235 nucleus with a neutron then leads to U-236, which is a heavier uranium nucleus, which very quickly undergoes fission. And the 4 types of nucleus reaction is 1, fission, 2, fusion, 3, nuclear decay, and 4, transmutation. Now, uses of uranium. Now, the high density of uranium allows it to be used as keel in the keel of yachts, those sort of sailing ships there, because of the density of uranium. It's used in the keels of yachts and as counterweights for aircrafts, control surfaces. And the other uses are highlighted in the nuclear uses and the chemical uses that are highlighted through the comprehensive presentation of this uranium. It's also used well for radiation shielding, in which U-238 plus 1 neutron yield now U-239 and 92-147 neutron. That is uranium-92. Well, all of them have uranium 92 atomic weight, but only the mass changes, and 147 neutrons. Now, how much uranium is in a nuke? Well, an impulsion fission weapon with an explosive yield of about 1 kiloton can be synthesized with as little as 1 to 2 kilograms of 2.2 to 4.4 pounds. 1 to 2 kilograms, which is the equivalent of 2.2 to 4.4 pounds. So with an explosive yield, we have this as little as 1.2 to 2.2, 1.2 kilogram, which is equivalent of 2.2 to 4.4 pounds of plutonium, or which are about 5 to 10 kilogram, or 11 to 22 pounds of highly enriched uranium. So as you could see from this, more uranium has to be used and less plutonium, which make plutonium more have to use little more plutonium to yield the same amount of energy as the uranium would have yielded in an atomic or nuclear explosion. Now fusion occurs when two atoms slams together, forming a heavier atom. Example, two hydrogen atoms coming together to form a helium atom, forming a helium fused atom. And this is the same process that powers the sun and creates a huge amount of energy. So that the sun, its comprehensive volume and appearance and mass, and that works by fusion. And it's the fusion of hydrogen to form helium atoms, and creating a huge amount of energy, several times greater than fission. So the energy created in fusion is several times greater than the energy created by fission. As you can see, fusion is more a building up process, and fission is more a decomposing process. And it also does not produce highly radioactive fission products. That is, the fusion doesn't produce radioactive fission products. So there we have a look at, introductory look at uranium. And from henceforth we are honoring my professor there at City College, Professor Morrow, who instructed me in Chemistry 103, 1978, and doctored me somewhere around in the 1980s when I requested my profile, my grades profile there, in which I had an A. So I said that he must have had a vision to have done that, and so here am I at this stage, 2024, doctoring Professor Morrow of City College. So we next look at plutonium, which is a more toxic and reactive element as compared with plutonium.